of the things you're going to be asked to do in dealing with continuity is finding points of discontinuity, or being able to determine intervals where the function is continuous. So remember, for continuity we have three conditions we're looking for. We want to find places where the function is defined, places where the limit exists, and places where the limit equals the function value. If any of those fail, then the function is discontinuous. Okay? So let's look at some different functions and determine their discontinuities, and also determine the intervals where the function is continuous. Okay? So in this first case, we're looking at a polynomial function. So f of x equals 4x cubed plus 2x minus 5. Okay? If we look at this particular function, we can see, first off, it's a polynomial, so I can put any value I want in for x, and I'm always going to get a real number out. So the function is always defined. Okay? And if we think back to what we did for finding limits, it doesn't matter what value I'm looking at, limit as x goes to 2, or -5, or 0, or 100, I can always find a limit. And more importantly, because it's a nice smooth curve, it is one that I know the limit is going to equal the function value at every single point. Okay? So here we can say there are no discontinuities. And if we look for the interval where the function is continuous, we can say it is continuous on the interval from -infinity to infinity. Okay? Let's look at this function g of x equals the square root of 2x minus 7. Now, unlike our polynomial function, we certainly know there are places there that our root cannot be defined. In particular, if we look at the inside 2x minus 7, we know that at 7/2 we're going to get a square root of 0, and if we look at anything smaller than that, this becomes undefined. Okay, so this one we would say is discontinuous for all x that are less than 7/2. Okay, notice here I didn't include the equals, because again, square root of 0 is just 0, and that is defined. Okay? But all of these values make the function undefined, which means they're all discontinuities. Okay? So if we're looking for the interval of continuity, we would say it is continuous on the interval. It's got to include 7/2, and it can go up to infinity. There's no restriction on the higher end of that. Alright, let's look at a couple of rational functions. Okay, so in this first one, f of x equals x squared minus 3 over x squared plus 2x minus 8. Okay, here the first thing we notice is that I can rewrite this function. This is the same as x squared minus 3 divided by, we can factor the denominator, so an x plus 4 and an x minus 2. So now if I think in terms of my conditions for continuity, I can see that my first condition will fail when x is -4 or x is 2. And everywhere else, it's going to be defined. Okay? We can check that the limit exists everywhere else, but again, if it's not a -4 or +2, we can see that, again, the function is going to equal the limit. So here, we can say this is discontinuous at x equal -4 and x equal 2. Okay. For the intervals of continuity, we can see that this is continuous on the interval from -infinity up to -4. We're not going to include -4, so that's an open parenthesis. Union -4 to 2. So all the values between those, but not including them. And then from 2 to infinity. Okay. In this other rational function, x plus 4 over x squared plus 4, Here we can see the denominator doesn't factor. And if I put in any value, this function is always defined. And you can try that. Plug in different values for x and you'll see you'll always come out with a real number. Okay? So in this case, this is a rational function that actually does not have any discontinuities. Okay? And again, we can check the limits, look at the left and the right at any particular point, and you'll see again that they do equal the function value. So for this one again, we would say the interval of continuity is again from negative infinity to infinity. Okay. The last two examples look at piecewise defined functions, which are some things that we're going to be looking at a little bit more as we move further on in this course. This first case, we're looking at g of x equaling x plus 6 when x is greater than or equal to 3, and it's going to be x squared when x is less than 3. Okay? Now for a piecewise defined function, we still have to look at the same three conditions, but we have to look at them in a different way. Okay? So just like what we did in all of these cases, for each function I need to think about, are there places it's going to be discontinuous? And then I need to check and make sure those work within the domain values here. Okay? The other thing I need to check is the actual domain boundaries. Okay? So what I mean by that is, if I look at this particular function, x plus 6 polynomial function, we already know polynomials are defined everywhere. There's no discontinuities. Same thing with x squared. So x squared again is polynomial, so there's no discontinuities there. So the functions themselves, we don't have any problems. But now when I look at the domain pieces, I have to think about, is the function going to be continuous along the domain? Okay? Well, certainly everything greater than or equal to 3 is going to be continuous, and everything less than 3 is going to be continuous. So what happens at 3? Okay? So here we need to check at x equal 3 if our three conditions hold. Okay? Obviously it's defined because I do have an equality here. Does the limit exist? This is usually the biggest question for these types of functions. So again, we need to check, does the limit as x go to 3 from the positive side of our function equal the limit as x goes to 3 from the negative side of our function? Okay. So here, I'm just going to look at each of these limits. The limit as x goes to 3 from the positive side means I'm coming in from the greater side of that. So limit as x goes to 3, I'll use the positive side, so x plus 6. And over here, the limit as x goes to 3 of the negative side, which is an x squared. And here we can see, again, we have polynomial functions. So the limit as x goes to 3 on the left side will be a 9. On the right side of this equation is also 9. So our limit does exist. Okay? And we can see that the limit will equal the function value, because when x is 3, g of x is going to be 9. So here we can say there are no discontinuities. And for our interval of continuity, it's going to be continuous on negative infinity to infinity. Okay? Alright, so let's look at this one. Same type of thing. F of x equaling x plus 2, x greater than 2 for the first part, and x less than 2 for the second part. Okay? So similarly to the last one, I can see x plus 2 and x squared are both polynomial functions, so I don't have any points of discontinuity there. For our second condition, if the limit exists, actually we can go back to the first condition. I can see here that I don't have equality in either of my domain pieces. So this tells me that x equals 2 is discontinuous because I don't have any spot where f of 2 is defined. Okay? Both are strict inequalities. Okay. We don't even need to check the limit existing at 2 because we've already said it's a point of discontinuity. And everywhere else the limit does exist, n equals the function value. So we can say our interval for continuity is from -infinity to 2, union 2 to infinity.